Greetings and welcome, friends. Welcome to the world of geometry. We are continuing our look with kind of constructing stuff and describing stuff and naming things. We're talking about measuring and constructing angles today. And first of all, we're going to have to define some things. All right. So first of all, an angle, which, by the way, notice how it's spelled, A-N-G-L-E. So guys, if you're ever trying to compliment a girl and you write her a note and say you're an angel, make sure you spell angel correctly and you don't call her an angle. That's just embarrassing. Or definitely don't get a tattoo that says my angle and then has a picture of a girl on your arm and it's spelled wrong forever. Man, that's unfortunate. That's definitely never happened to me. The angle is a set of all points consisting of two different rays. So rays have a starting point and then they travel infinitely. And the rays have a common endpoint called a vertex. So here's our vertex, and we've got the ray AB and the ray AC over here. The rays are called the sides of the angle. So this angle is kind of this composite of two rays, and this is an angle. All right, that's what we're talking about. Now, in terms of naming angles, because once again, the notation in which we use to communicate about mathematics is significant, and we want to be consistent in the way that we use math as a language. There's actually a bunch of different ways you could name this angle. First of all, notice this new little symbol. That guy right there. That means angle. All right. Try not to make it look like a less than sign. All right, so the bottom of it is horizontal, and definitely you're doing really poorly if you make it look like a 7. Then you just rotate it. Yeah, no, don't do that. So that symbol means angle, and you can name an angle using its vertex. So you could say angle A, and based on this diagram, you guys would all be like, oh yeah, there's angle A. I see angle A, the angle with the vertex at A. You can also use a point on each ray and the vertex, where the vertex must be the middle letter. All right, so this is kind of more the formal name. Sometimes we sometimes have to use the full name for the angle. I'll show you a case in which we won't in a moment. But so angle BAC. All right. The middle letter is indicating where the vertex is. If I said angle ABC, the angle that I would have been referring to is this angle. And that is not the angle that you're talking about, right? This is the angle that we're talking about here. So the order in which you label these matter, all right? So there's a lot of potential for just mistakes with mislabeling angles. You could also call it CAB, right? So C to A to B. So you could kind of have the reversal on that name, and it's just as sufficient. But yeah, the A's definitely got to be, you either name it just by the vertex or by its full name. You can also, sometimes angles will have a number just thrown in their armpit right there, and you can just call it by that number. So angle 1. Perfectly good. And now all of these are talking about the actual object, the actual set of points, the actual diagram that we're seeing. That's what all of these are referring to. So these are not referring to the size of the angle, some numerical value measuring the angle. This is just the object itself. All right. And the reason when you'd have to use one of these, what if I had multiple angles with this same vertex? What if I also had over here point D, and then what if I also had here point F? If you just said, hey, look at angle A over there, I'd be like, what are you talking about? Are you talking about CAB? Are you talking about BAF? Are you talking about DAB, this bigger angle that happens to overlap this other one, right? Or this entire, right? There would be uncertainty because you weren't specific enough with the name. So those are the situations in which you need to use the formal name for your angle. Now, in terms of the angle, you could also think about the points that are between the sides of your angle as being the interior of your angle, and the region outside of that as being the exterior of your angle. That language doesn't show up a whole lot, but I figure we can mention it. All right. Ooh, let's practice naming angles. Ooh, I'm excited. Here we go. Naming convention. Let's see. I'll scale down. 80% seems good. Yeah, I think that was 81% by the time I deselected that. A lighthouse keeper, for fun, measures the angles formed by the lighthouse at point M and 3 boats. I guess that's also valuable. They'd probably talk more about like coordinates, viewing angles, or north of east. That might be something that they'd mention, or south of east. Sure, who knows? It says name the 3 angles shown in the diagram. All right, first of all, do you guys see 3 angles here? Let's see. Yeah, could someone give me the name of one of these angles? Well, those are rays. So I could have angle JML. All right, so that would be the macro angle. Angle KML. So that would be like this littler angle. And JMK. And there's other ways that you could have also reversed those letters, and that would have worked as well. Now notice I'm labeling these with like arcs, or double arcs, or triple arcs. Arcs are used in diagrams to note congruence of angles, just like how we had tick marks, to measure congruence for segments. These arcs, or double arcs, or triple arcs, or more than that, would signify when angles are congruent to each other. And I was just using that to also point out that these are 3 different angles, and I do not know whether or not, like, for instance, these 2 are equal in measure. Yeah. Let's see. Here we go. Let's talk about measuring angles. Measuring. So we can talk about the length of a segment, but you can also talk about the measure of an angle, which would be kind of like how wide it is open, is I guess how you could describe it. A protractor is a tool that we will use to do that. Sometimes angle measures will be given to us, and a typical unit of measure is in degrees. And in terms of degrees, you guys probably are aware of how many degrees are there in a circle? 360 degrees, which is a somewhat arbitrary unit of measure that goes back even as far as the Babylonians and their mathematics. It's probably related to the world that we live in, just like we use a base 10 number system, probably related to the fact that we have 10 fingers. 360 is most likely related to the number of days it takes for Earth to revolve around the sun. Or something thereby close to that. There's also some interesting theories as to maybe the Earth used to take 360 days around the sun, which is weird to think about. But yeah. So there's some thoughts about that. I guess also some, apparently, like, multiple ancient cultures also had 360 days roughly as their calendar measure before, but anyways, there are other types of measurements that you could use, which, by the way, Ryan, you can unplug your headphone jack. The other ways you might, besides degrees, later on in this course, we'll mention radians briefly. Radians, A-N-S. And then there's also grade, which is given as a like percent, right? You might see that on like the side of a road or something, like 8% grade for a hill or something like that, and that's kind of like, I think 0% would be flat, and I think they describe 100% as like complete steepness. So like, in something between that, it'd be like the percent of the way. But either way, most of the time we talk about degrees. What did I just do? Did I just delete stuff? I did. There we go. Wow, I didn't even know I had that possibility. I just hit the backspace key. How did it know what to delete? Did it just delete everything on my screen? That's bizarre. Or probably the whole layer? That's probably what it was. Just like we had the ruler postulate, which postulates, you guys might recall, were things that you just need to accept are true. Just like, get over it, okay? It's true. Move on. All right. There's also the protractor postulate. Consider OB and a point A on one of the sides of, right, OB, the line. Here, let's see, point A. Wait a minute. Consider line OB and point A on one side of OB. I'm not sure what they mean by... okay. All right, they're saying the entire line and A is in like above or below. That's what they're referring to, side. I was like, what do they mean by side? You don't have sides of a line, but now I get you. Okay. The rays of the form OA, right, can be matched 1-to-1 with the numbers, the real numbers, between 0 and 180, right? So 0 degrees, 90, all the way to 180. So just like we had a number line, you could view this as like some sort of number arc, where a full circle would have been 360, as we said, so therefore a half circle would have been 180. And if I correspond my angle, its vertex kind of being at the center of this semicircle and one of its rays matching up to 0, I could then look at a measurement that would describe, right, numerically, how open is this angle. And that would be a number that is referred to as the measure of angle AOB or BOA, and it can be written as M of angle AOB. So notice this little notation, throwing an M in front of our angle. This is now referring to a number. So this is a number, all right? Whereas angle AOB is a picture. It's the object, right? The actual angle. And the measure of angle AOB is equal to, hey, we've heard this language before, the absolute value of the difference between the real numbers matched with OA and OB. So in this case, in this picture, that would have been the measure of angle AOB is equal. I use equality to describe numbers, right? This is a number. Would have been the absolute value of 140 minus 0. And so I would call that 140 degrees. All right? And just like the ruler postulate worked when I didn't start counting at 0, likewise, I can do the same thing here. I don't have to have one of my rays lined up with 0, and the protractor postulate will still work. And then we decided to, as humans, we like to categorize things, and we categorized angles into a variety of different ones. Let's see, is your headphone jack still plugged in there, Ryan? It looks like it might be. So here we go, types of angles. An acute angle. Oh, adorable. Measures greater than 0 and less than 90 is acute. All right, a right angle measures 90 degrees. This is somewhat our definition. We will be using that definition in theorems or proofs later to prove theorems. So I might say def of right angle, therefore this angle measure is 90 degrees. You also can see that I can note a right angle with this little square in the corner, right in its armpit. That means it's a right angle, and therefore its measure is 90. An obtuse angle is an angle that's between 90 and 180, right? So if 90 would have been here, this angle is obtuse, and a straight angle measures 180 degrees. So we can put angles into like little families like that, because sometimes it's convenient to communicate and kind of group them as such. Let's see. Here we go. Example dos. Ooh, man, I love the way my inverted colors show up on this. It makes me feel like the Omni tool in Mass Effect, which, by the way, Mass Effect Andromeda coming out next month, I believe. Yeah, nice orange. Classy. Find the measure of each angle, then classify each angle. So GHK. GHK. Actually, tell you what. Let's use some colors. Color. So GHK is this angle. And if I want to find the measure of angle GHK, we'll write it out formally, and then eventually we'll just be like, yeah, you guys can read it yourself. It looks like, so GH corresponds to, you could look at this as 180, but notice they actually count both ways. I'll correspond it to being 0. And where does the ray HK point to for the outer set of numbers? There's 120, there's 130. Looks like 125. So that's going to be a 125-degree angle. And if that's its measure, how would you classify it? Obtuse, right? Nothing too difficult, right? No es más mal. Let's see, JHL. So looking, starting at J, going to H, and then up through the L, right? So that's this angle. And you can probably tell just by reading that 90 minus 0. Or, like I said, you could also actually do 180 minus 90 is still 90, whichever way you think about that. So the measure of angle JHL is 90 degrees, and that is so right. And let's see, lastly, LHK. I'll just sloppily, right, label it like that. So the measure of angle LHK is now going to represent a number, and I think I could either do no, I was completely wrong. I was looking at my actual line. 125 minus 90. And then absval. Or I could even do 90 minus 55. Right? Both of those should correspond to the same thing. Looks like that's going to be 35 degrees. And that is acute. Right, so nothing too fancy. I think you guys would agree. And just like we had measures of segments, numerical distance that we were talking about, we can also have measures of angles, and those measures of angles, when there's multiple angles, I could then compare them, and if two angles have the same measure, you could probably assume that means the angles will be congruent. All right. And once again, notice the consistency in the logic here. Numbers are equal, or numbers can be equal, and geometric objects or figures can be congruent. All right. And so the definition of congruent angles, def of Kong, I'll use that all the time. If their measures are equal, then the angles are congruent. And vice versa. If the angles are congruent, then two angles' measures must be equal. All right, so that's not that bad, right? Very similar logic, consistent logic when we were talking about segments. If two segments have the same length, then these segments were congruent. All right, ooh, and this is what, if you've ever done any quilting, you know you've been applying, no, I can't even finish. Anyways, identify the congruent angles in the quilt design. It says the measure of ADC is equal to 140. What is the measure of angle EFG? Now, notice the double arcs. That means that angle ADC is congruent. That's what those double arcs mean to angle EFG. And if the angles are congruent, their measures are equal. Therefore, the measure of angle EFG equals, right? So congruence for figures, equality for numbers, 140 degrees. Also, I didn't do the thing, part A. Crazy Mr. Waddy. Let's see, part A, identify the congruent angles labeled in the quilt design. I guess I did this part of it. What's another pair of congruent angles? And actually, let's label them with our shorter names for them. We don't need a full three-letter name. Yeah, angle G is going to be congruent to angle B, right? And even though they're like completely different quadrilaterals, you can still have congruent angles right within those, and that's perfectly legitimate. And guys, you're probably seeing all the symmetry today, just like we had segment addition postulate, and I've mentioned area addition postulate. Guess what? Angle addition postulate. That's a thing. I don't think I need to summarize too much here. Basically, the big angle is equal to the sum of the two smaller angles. Right? Chop, chop. And then you know where this is going. They're going to throw some algebra in your geometry. You know, that's what they do. That's what we as mathematicians have done for generations, I assume. Probably pretty sure. Unless, I don't know if that came up about in the days of integrated mathematics. Who knows? Let's see, given that angle LKN, that's the big angle, is 145 degrees, find the measures of these two smaller ones. All right, so using angle addition postulate, I'm going to say that this plus that equals that. All right, so I'm going to write an equation that corresponds to that. 4x minus 3 plus 2x plus 10. I could throw parentheses around this, but I don't have to because this is plus. If that was minus, then it'd be important. Is going to equal 145 degrees. And now I can combine some like terms. 4x plus 2x. Right, and then it's just like our old school algebra days. It's as comfortable as wearing sweatpants. Like, oh man, I remember this. 10 and negative 3, that's definitely 7. Equals 145. We'd subtract like the 7 from both sides. And let's see, we'll have 6x equals 138. Using subtraction property of equality. Now using division property of equality, just divide both sides by 6. Does this come out evenly? Who knows? I'll ask my 23. Well done. So if x is 23, now I can substitute it in here and here, right? To find the corresponding angles, because they didn't want to know x, they wanted to know what those angles were. Yeah. So the measure of angle LKM is going to equal 2 times 23 plus 10. So that's 46 plus 10, or 56 degrees. And I could actually, like I said, plug it in here, or I could just now take 56 and subtract it from 145 to find the measure of MKN. Right, so 145 minus 56, 89 degrees apparently. And I label my units, angles. We're measuring these right now in degrees. Like I said, there will also be in the future radians and all sorts of other things. Last concept is the fact that we can bisect angles, just like we had segment bisectors. You can also have angle bisectors, which would be any ray, line, plane, I guess even, that is going to divide an angle into two congruent parts, which you can see they're labeled congruent with their single arcs. And if the arcs are congruent, if those two angles are congruent, then their measures will be equal. So YW, the ray or the segment or the line, are said to be angle bisectors. And we're gonna pause there. So thanks for watching, internet friends. Bye.